Welcome back, class. So lastly we learned about the spectrum analysis or frequency response analysis of the BJT and MOSFET amplifiers. We developed the small signal models and we analyzed that if we have different kind of series for parallel coupling capacitors, okay, for example at the input side, at the output side, or like around across the emitter, then what will be the effect of these different kind of the capacitors on the spectrum of the amplifier. So these capacitors are basically called as the external capacitors. External capacitors, okay, and they are basically mostly used for the low frequency analysis of amplifier. Okay, they are used for the low frequency analysis. But as we know that basically a BJT is formed by the junction of the P and N type materials. Okay, let's say we have P and P junction. So we get two junctions here, one for PN and one for this PN. Okay, so basically we have some internal capacitance of the amplifiers, okay, which is also called as stray capacitance. Okay, that what is the capacitance among the junctions, and like if we are making some connections with this junction, okay, so due to these wirings and the internal junctions of the BJT, okay, or MOSFET, okay, we have stray capacitance. Okay, the value of the stray capacitance is usually very small, in the range of picofarad. Okay, so now we are going to analyze the effect of these internal capacitance, okay, in the amplifier, okay, and how it will affect the spectrum analysis or the response of the frequency response of the amplifier. So we know that one thing, that the capacitance is inversely proportional to the frequency, okay, or we can that frequency is inversely proportional to the capacitors. So when the capacitor value is very small, okay, capacitor value for example in picofarad range is very small, so the frequency will be very high. Okay, so because of this reason, this analysis is called high frequency response of amplifier. Okay, high frequency spectrum analysis of the amplifiers. Now we are going to develop an expanded small signal hybrid pi model. We know that how we can make the pi model of the an amplifiers, but now we will look into a more detailed version. Okay, so first we will learn that how we can make this hybrid pi model, then we will learn how we can analyze that. Okay, so the analysis techniques are same which we have learned so far. So let's say this is a simple BJT. Okay, this is base terminal, this is collector, and this is emitter terminal. Okay, so as I said earlier, we have two different junctions of the PN or NP materials. Okay, so based on those junctions, and if you remember, okay, the simplest model, the pi model of the BJT, we draw like this, that we have our pi, okay, and the voltage drop here is V pi, okay, and if the like the emitter is ground, so this is ground, and here we have the dependent current source with the value of Gm times V pi, right, at the collector side, and this is my emitter point, which is usually ground. Okay, and here we have output resistance R. Okay, this is the simple pi model of the BJT, okay, which we have learned earlier on. Okay, so this is my base terminal. Now basically there will be two internal capacitances, okay, of the amplifiers. So one will be across the base and emitter junction. Okay, so base and emitter junction, if you remember, it's usually forward biased. Okay, it's working in forward bias, and base collector junction is working in reverse bias, so that the normal operation of the amplifier is being held. Okay, so base emitter junction, okay, it will have some capacitance, and we will model that capacitance, okay, using a capacitor here. Okay, and we refer this capacitance as C pi. Okay, similarly the base collector junction, okay, so that will be reverse bias junction, right? Base collector, this is forward bias, base collector junction, it will be reverse bias. So base collector junction, it will also have a capacitance, internal capacitance, which we called C mu. Okay, so this is my base point, this is my collector point. So that capacitance will be coming here. Okay, we call this C mu. Okay, so this is the basically the hybrid pi model. Okay, by incorporating the effect of the internal capacitances. Okay, so C pi is the forward bias junction capacitance. Okay, forward bias base emitter junction capacitance, and C mu is the reverse bias base collector junction capacitance. And as I said earlier, this value is usually in picofarad range. Okay, and one more thing is, usually the value of the C pi capacitor, okay, is much greater than the C micro. Okay, and basically we know that this is a general rule that the capacitance of a junction, okay, can be represented in terms of the epsilon all, okay, material properties, and the thickness of that junction. Okay, so basically capacitance is inversely proportional to the thickness of the junction. And if we are moving, for example, towards the reverse bias, okay, we are moving more and more reverse bias, so then the thickness of the junction in the reverse bias, it could be increasing, right? So if the thickness of the junction is increasing, more and more reverse biased, okay, then the capacitance will be decreasing. Okay, so that's why usually, because C mu is basically the reverse bias capacitance, so its value is usually very low as compared to the forward bias junction capacitance. Okay, this is general rule. Now we get this hybrid pi model, and earlier we have learned that if we don't have these two capacitances here, we can easily analyze our AC model. Okay, AC small signal model, small signal circuit of the amplifier, and we can get the frequency response. Okay, but now if you look at this circuit, okay, now basically the addition of these two capacitances have made our circuit complex. Okay, so now we have to analyze this circuit. So basically first we will try to simplify this circuit. Okay, we will try to simplify this circuit, and once we get a simplified circuit, then we will simply apply the techniques which we have learned earlier on. Okay, so we will simplify this circuit, okay, these two branches, using a Miller theorem. Okay, we will simplify this using Miller theorem. Okay, so let's see what exactly the Miller theorem is and how by using that we can simplify our this circuit. So Miller theorem basically related to the two-port networks. So for example, if you have a port A and if you have a port B, okay. So basically like you have a circuit, okay, like and this is giving something, okay, and this complete circuit is basically referred as port A, and there is another circuit which is referred as port B. So if you look at this pi model, so basically between base and collector junction we have included C mu. Okay, so this is a kind of our port A, and this is our port B. Okay, and in between them we have this capacitance. Okay, or we could have any kind of like lumped component, resistance, capacitance, inductor, and generally we represent using an impedance. Okay, so I have port A and port B, and in between them I have an impedance which could be representing any lumped component. So from port A the current IA is flowing and the voltage drop here is VA. From port B the current IB is flowing and the voltage drop is VB. So basically using Miller theorem, Miller technique, what we can do, we can draw the equivalent circuit of this. And what is the equivalent circuit? Basically we can divide this impedance into two parts. One impedance with this port A network, which we call Z1, and one impedance with this port B network, which we call Z2. Okay, so basically this branch between the two ports, between the two port network can be removed, and it can be replaced with two impedances Z1 and Z2. Okay, so that is the Miller theorem. Now the question is, okay, we can replace them, then what will be the value of this Z1 and Z2? So basically this Z1, it can be written as this impedance divided by 1 minus second port voltage divided by the first port voltage. Similarly Z2, it can be written as Z impedance divided by 1 minus this port impedance divided by this port, this port voltage divided by this port voltage. So these are the general formulas, okay, of the Z1 and Z2, that how we can actually convert this impedance into two impedance with these values. Okay, its proof is very simple. Okay, for example, if you look at the figure 1, okay, so what we are getting here, focus here please. So this is, if we apply the KVL here, so input voltage, it will be equal to the voltage drop here, so IA times Z plus the voltage drop here. Okay, so this will be the simple KVL equation here, right, for the VA. Or what I can do from this, I can write IA, that will be VA minus VB divided by Z, right? Simply I can write IA like this. Now look at this figure. So from this, if you notice, we can also write IA as, okay, voltage divided by its impedance, like voltage drop divided by impedance, V over R, okay, that is my current. This is my second equation. Okay, so basically this current and this current are same, so it means VA minus VB over Z is basically is equal to VA over Z1. Okay, or what we can do, that Z1, okay, it will be equal to VA times Z divided by VA minus VB. Okay, and if you take VA common from the bottom, okay, if I take VA common here, so it will become 1 minus VB over VA, and here I have VA common. So this VA, the VA will be cancelled. So I will get Z1 will be Z over 1 minus VB over VA. Okay. Similarly, we can prove this one. Okay. So the basic thing which we learned from Miller theorem is that the interconnecting impedance can be divided into two impedances, and its values can be calculated using these formulas. Okay, that is the basic things. Okay, now let's assume, okay, let's assume that we have that this Z value is for one capacitor. Okay, so it will be 1 over j omega c, right? And let's say this Z1 is also representing a capacitor, okay, and its impedance can be represented using this one, right? So what is our Z1? Z1 is Z over 1 minus VB over VA, right? So what is Z1? 1 over j omega c1, right? So 1 over j omega c1, and what is this? 1 over j omega c divided by 1 minus VB over VA, right? So that will be equal, and basically this j omega will be cancelled, and if we do some rearrangement, so we can get basically c1 will be equal to c times 1 minus VB over VA. Okay, so basically this capacitance value, okay, this capacitance value C1, okay, it will be equal to this capacitance value, okay, multiply 1 minus VB over VA. Okay, so if we have a capacitor here C, so we can divide that capacitor into two parts, C1 and C2. So C1 will be equal to C times 1 minus VB over A. Similarly C2, it will be equal to C times 1 minus VA over VB. Okay, just vice versa. So this is the main equation. Okay, So using Miller theorem, if we have a capacitor here, we can divide that capacitor into two parts. Okay, one with here C1 and one into C2, and value of C1 and C2 can be calculated using these formulas. Now next is how we can actually analyze. Okay, now come back here. Everybody please focus. So this is my the capacitance between base and collector. So I want to remove this capacitor. Okay, so this is basically and we know that we can convert this into two capacitors, C1 and C2. And C1, it will be equal to 1 minus C1 will be equal to C times 1 minus VB over VA, right? And C2, it will be equal to C times 1 minus VA over VB, right? So C1 will be equal to, what is C? So C is basically C mu here, right? This capacitance, C mu. 1 minus VB. So what is the base voltage? Base voltage is the voltage drop here. Okay, so base voltage is basically V pi. And what is the collector voltage? Collector voltage is basically the output voltage. Okay, that is the voltage drop here. Okay, so basically VB is V pi divided by V out. Okay, so that will be my C1. And similarly, we can write the C2, and C2 will be C mu 1 minus, okay, VA, okay, the port A, and port A is basically VB. VB is basically port 2, so it will be V out here and V pi here, okay, and it will be V pi over V out here. Okay, so C1 is also called as CM, okay, or Miller capacitance. So basically, if we draw the equivalent circuit, so this equivalent circuit can be replaced like this, that I have a capacitor C pi here, okay, and then I have this C1 or CM capacitance. Here we have dependent source, okay, and here I get C2 capacitance, okay, and we remove this part here. Okay, this is R pi, this is C pi. So this C mu can be divided into C1 and C2. So once we divide them, okay, then our circuit becomes simple as like the earlier one, and we can analyze this circuit to get the frequency response analysis of the with the high frequency components with the inclusion of the stray capacitance. Okay, so we will solve the relevant example in the live session. Thank you very much for your time.